Hello, everybody. We're gonna get started. By now, I think you know this is Sigma. I'm going to be talking today about distributed leader election, which we'll get to that. But first, we want to do some introductions. First, we're going to go through and introduce ourselves, and then we'll have you guys, and just like introduce yourself, say your name, things like that. But we're going to start with us.
Name, pronouns,
Name, pronouns, icebreaker question.
Good icebreaker question.
Tell people to say a fun fact about themselves if they want.
Sure.
Okay.
Fun fact.
Okay. Yeah, so we're gonna start out with admins, in no particular order. Well, actually,
Join.
start by joining the Discord if you haven't. I'll leave this up for a second, just in case. Okay, yeah. Okay, so first, my name is Porter. I just started as a master's student, the BS MCS combined program. I also minored in math, which is why I'm here for Sigma. I like math and computer science. I interned at Palantir over the summer, and I'm taking CS 473, which is that algorithms math class, which I don't know, it's interesting. It's kind of related to what we do. So if you like this, you might keep that in the back of your mind. And this is my fourth semester as a Sigma admin. And also completely unrelated, I'm kind of fun fact, the captain of the triathlon club here on campus. So if you like to swim, bike, or run, you should come talk to me.
Hi, I'm Ian. I'm a junior in statistics at CS. I am a CA for CS 473, which is the algorithms class. This is my first semester being a Sigma admin, and I do research with Tandy and George in network science.
All right. Hi, everyone. I'm Sasha. I'm a double major in CS and physics. So I'm also a course assistant for 473, as well as for 374. So if you all ever end up in that class, it is required for probably most of you. You might see me there. It's my third semester as a Sigma admin. I do research in quantum photography with Dakshita Kirana and also kind of Macron now. And also, I recently founded a Queer Coded, which is an org for LGBT people in CS. So if anyone is interested in joining that, come talk to me. All right.
I'm Franklin. I'm a senior in math and CS. Interned at math this summer. I'm not seeing any classes. I used to see 374. I'm taking randomized algorithms with Sasha, and Ian shows up sometimes. This is my third semester, I think, as a Sigma admin. On the side, I like to do better programming. Very cool. ICPC.
Yeah, so I guess now it's time to get started. I don't know if you guys want to like sit down or something. Yeah, so basically kind of the format of Sigma is like a person will come give a presentation every week just about some interesting topic in math or CS or both. And then we just, I don't know, just kind of talk about it. And if you want to give a presentation, come talk to one of us. That's one of the main parts of Sigma is kind of learning a topic that you're interested in and giving a presentation on it. It's a really great way to learn the topic, and it's also like just kind of interesting to be a part of the club. So just quick plug for that. What I'm going to be talking about is leader election for distributed systems, which is a topic that I'm interested in. I've taken a few classes, CS 425, and right now I'm in CS 539, which are both distributed classes, which just distributed computing basically at a high level is like different computers talking to each other in a like that are distributed all over the place. So to kind of get into more of what that actually means, this is a definition that I stole from Indy, a great professor. Highly recommend taking CS 425 if you ever have the chance. But he said distributed computing is a collection of entities, each of which is autonomous, programmable, asynchronous, and failure prone, and which communicate through an unreliable communication medium. So that's like a lot. But I think there's a few things in there that are pretty interesting. Does anybody want to venture a guess? Like what are entities referring to? What could be an example of an entity by this definition?
A computer.
Yeah, yeah. A computer, you could have like different computers in different places talking to each other. Or another example could be like different cores on a multi-core processor. Autonomous just means like autonomous programmable. It's kind of like it's its own agent that's working together with other unique agents to come up with some emergent behavior. Failure prone is another one that like maybe this computer will just turn off. If you have a big sprawling system, like you don't know what's going to happen. So anything could go wrong. So you have to, there's a lot of different like intricacies of like, you have to be ready for anything basically, because anything could happen because such a big system. Asynchronous is another challenge of distributed computing because it's not one central computer that's looking at one clock. Everyone has different clocks. Things are happening at different times. If you send a message over the network, maybe it won't arrive. Maybe it'll take a week to arrive. Probably won't actually take a week to arrive, but in theory, and that's why we're here, is the theory of computer science. In theory, anything could go wrong. Yeah, unreliable communication medium. So yeah, some examples, we talked about this a little bit. Cloud computing is an example of distributed computing for two reasons. In a data center, there's many different computers that have to be able to communicate with each other and provide a service, like Google Docs or something. Like there's a lot of computers involved to make that happen, and within the data center, and it has to communicate with you externally as the user and between data centers to have like Google Docs doesn't run only in Vermont or wherever they have servers. It's like they have different things stored in different places and they have to work together to provide a reliable service to the user. Multi-core machines, there's in your computer, there's maybe different processors running at the same time. But to you, there's only like one user interface. So they need to work together to provide one consistent program, basically. And then also just like really wide definition, like any public networks, those are like kind of distributed systems if you think about it. Like even the internet is a distributed system because there's different agents communicating over an unreliable communication medium. Blockchain, crypto, that's an example. Tor routing, which is just a, I don't know, internet routing scheme that uses multiple computers to kind of anonymize your information. And then Napster was a famous one that was like illegal about like, I think it was music, like stealing music. There was like, you know, in the early days of the internet, like it's a distributed, what it is it's a distributed program. We have like many people can log into this network and like provide their own PC, give like a little bit of computing power to this like big wide network. And the more people you have just like uploading songs and sharing their computer, like then you can basically have a really distributed repository of illegal music so that anybody can join this network and get any illegal music they want. And I actually had a cousin who, when she was little, she was using LimeWire, which is kind of a similar idea, and which is, you know, illegal music service that you shouldn't use one of these. But she did.
Soul seek instead.
Yeah, anyways, the FBI showed up at my cousin's house. So yeah, I don't know. I've never heard of that happening to anyone else, so that's pretty unlucky, I guess. Yeah, what's up?
Is that like the same idea as torrenting?
It's very similar. The structure of the network is kind of different. I think the main thing that's different, if I remember correctly, is Napster has like a centralized, like there's some centralized servers that a company needs to run for introduction of like when you join the network, making sure that everyone else knows that you're on the network. I think that's the distinction.
Technically, that is also true of BitTorrent, but most modern torrent clients solve this using an ancillary protocol that uses a distributed hash table.
Wow. Yeah, okay, so common challenges. I'm mentioned some of these a little bit already. No synchronized clocks. It's hard to coordinate things if you don't know when something is happening. There might be a large number of hosts within a data center. You might have hundreds or thousands of computers, many data centers. The internet is billions of devices, so there's a lot going on. Failures is a challenge because like if you try to send someone a message and they don't respond, is it because the network is slow? Is it because that node failed? Is it because they chose to not send you a message, or maybe they're sending you malicious messages? There's so much that could fail. So you really have to be ready for anything. yeah, network challenges. The network is really variable. Everything is different. So anything could happen. So you really have to be, when you actually implement these systems, you have to think about a lot of edge cases. What we're going to be talking about today is who gets to make decisions in distributed systems. So if you have like a network of many computers, sometimes it's useful to have one specially designated node that gets to make decisions. Does anybody have any questions so far? Okay. Yeah, so leader election, we're going to start with a simple version. So like I'm saying, it's often to have one specially designated node for a variety of different reasons. One reason is maybe some algorithms, like most distributed algorithms have to start somewhere. So having one node that starts the algorithm is kind of required sometimes. If you have different data centers, you don't want to have like every individual computer sending messages to every individual computer in another data center. You might want to have one or a few nodes designated as like the communication node. Sometimes there's like some computation in an algorithm that only needs to happen in one computer. So why have every computer do it? You can just designate one node to be the node that does that computation. So our goal is try to elect one single leader upon which all non-faulty processes agree. So basically select one special blessed node as the one that is the leader, and everyone else has to know that they're not the leader. And then just a little caveat, many different nodes could call for an election simultaneously because this is a really complicated system. If we know that this is the one that's going to start the leader election, then we could just say that node is the leader, and then we don't have to do an algorithm. So at any point, any node could say, okay, let's call for an election. And the result should be the same, or we at least should be able to come to some kind of consensus on who the leader is. Any questions with that? So the model that we're going to be looking at for now is ring election. So we're going to say all of the computers in our distributed system are organized in a logical bidirectional ring. And they might not be physically connected. So that's what I mean when I say logical. Like on the internet, pretty much every computer can reach every computer. Not exactly, but that's kind of true to an extent. So sometimes it's useful to like impose our own organization of like even though any single like I don't know, this node could reach out to this node because they're both on the internet. We're just going to say for the purpose of simplicity and coming up with this algorithm, only this node will communicate with its neighbors. And we're not going to get into I'll talk a little bit about it later, but determining how you organize this ring is not what I'm going to talk about right now. Just assume we have some ring of these nodes will only communicate with their neighbors. They can send messages either way, like to and from each other. And then we're also going to assume asynchrony or no node or link failures. So when I say asynchrony, sometimes like there are different models of distributed computing and like at the theory level. Synchronous distributed computing is you kind of like assume all of these nodes have some concept of time. So that might be useful for like determining if some node had a failure. Like if you say they don't respond within 3 minutes, it must have crashed. But we're going to assume asynchrony. So at any point, some node could, well, okay, we're also assuming no failures. So it doesn't exactly apply. But if there were failures, asynchrony would kind of be important if, like if some node, if we don't receive a message back, we can't say like necessarily this node crashed because it's asynchronous, but we're also assuming no failures. So just to make it simpler. Okay, so first question, kind of this like first theoretical question is like, is this even possible? So I have this true or false question. If processes are identical, no deterministic algorithm can solve leader election in a ring. Does anybody have an idea if this is true or false? Or have any questions about the question if it's not clear? Is this true or is this false? Yeah.
What was the condition for being correct?
Having one node say that it's the leader and have everyone else say that it's not the leader. Yeah.
I assume you can't assign like attributes to any node outside of the process.
Good question. Yes, you cannot do that for this true or false question. So every node, if some node has an attribute, because it's identical to all the other nodes, every other node also has that attribute. Yeah.
Might be true because there's not really like a way to break the tree.
Exactly. Yeah. So it's true. I'm not going to do like a rigorous proof, but the idea is kind of if every node has the same initial state, and every node, if they're identical, they're all sending the same messages. So if every node sends the same messages, every node will receive the same messages because it's a symmetrical ring. So then no node can be different than any of the other nodes. And to have a leader elected, you need one node to be different. So this is kind of like a theoretical thing. Like you're not really going to have computers that are exactly different from each other, or all exactly the same, because there's, you could have every node generate a random number, for example. And then they would have different attributes. So then you could say maybe the highest random number is the leader. But then that's not deterministic. So in reality, you can have computers generate random numbers, or at least pseudo-random numbers. So this question is more of a theoretical question, but I think it's still kind of interesting to think about that. So kind of like what you're mentioning with attributes, we're going to assume each node has a unique ID. Maybe we assign those IDs somehow, maybe they were randomly generated, but just assume each node has some unique ID, and then the problem becomes solved. Okay, so the first algorithm I'm going to introduce is the Chang-Roberts algorithm, which is fairly straightforward. It just says send IDs clockwise, just one direction around the ring, and only relay smaller IDs. So if you receive an ID that's higher than your ID, just ignore that message. If you receive an ID that's lower than your ID, send it forward. If you receive your own ID, output leader and send terminate around the ring. If you receive terminate, output not leader and continue forwarding this terminate message around the ring. So if you think about it, like you're sending only the smaller IDs. So if you think about like, okay, the node with the smallest ID will send its message along, and that message will keep propagating throughout the whole ring because there's no ID that's lower than that. So it'll keep propagating all the way around the ring until it gets back to the lowest ID. So then that node that has the lowest ID decides it outputs leader. So it decides that it's the leader and it terminates the program because it decided it's the leader. And it sends terminate around the ring again because it's at this point, it's the only one that knows that it has decided that they're the leader. So then it has to tell everyone else that they're not the leader by sending this terminate message. And then if you receive a terminate message, it's because the leader that elected itself sent you the terminate message. So if there's a leader that sent that, you can't be the leader because the leader already exists. Does that make sense? All right, cool. So this is just like the same exact thing, just like you can write it in another way. I think one thing that's kind of interesting about this is in distributed programming, there's often often it's not more clear to write pseudocode. Like if you compare like this version of the algorithm, I mean it's the same algorithm, but this representation of the algorithm is 3 bullet points and it's fairly straightforward. And then this is like, I don't know, 10 lines of pseudocode, which this still isn't particularly confusing. At least if you've seen pseudocode before, I don't know, maybe some of you haven't. But I think it's like sometimes it's often enough to not like when you're describing a distributed algorithm, it's often enough to just not even write the code at all, just kind of describe it in a way that kind of makes sense. And sometimes that's actually the best description that you'll see in like academia. Okay, so this is just like a little brief different thing. I said before, output leader or output terminate or output, oh, sorry, don't output terminate. Output leader or not leader. But when I say output, who are you actually outputting to? Yeah.
I mean, presumably some other part of the program you're running?
Yeah,
Presumably
Yeah.
this is the first step in some sequence of actions where
Right.
you require a leader.
yeah. So it's kind of a trick question. Because
Yourself,
Yeah,
technically.
it's kind of yourself. It's kind of like the output is almost like the general consensus among the system that everybody needs to know this information. Everybody needs to know who the leader is or that they're not the leader. So yeah, the output is to the next program or a different part of the program or quite likely I don't know, there was some program that needed to decide a leader. So it's like a higher level program that called down this leader election program. And then it comes up with who the leader is and just outputs that to the upper level program that needs to know who the leader is. And I guess I've been a little bit abusing the way that I'm talking about this. This technically is outputting not leader. It's not outputting who the leader is. Like all these other nodes don't know who the leader is. They just know that they are not the leader. But this algorithm is easy enough to modify to make everybody know who the leader is. Instead of sending terminate, the leader could just send their ID, or like elected the leader with this ID, and then everybody would receive who the leader is. So for this case, it doesn't really make a difference, but that is a distinction that you might want to draw sometimes. Like maybe not everybody knows who the leader is, they just know they're not the leader. Okay, so to make the like kind of formalize the idea of correctness, for this context and for other contexts, in distributed computing, we have a few things called safety and liveness. Safety is the idea that something bad will never happen. Like I don't know, it's a weird use of the word, but and it seems actually surprisingly not formal, given that this is like the formal definition of like correctness is like safety and liveness. And okay, saying something bad will never happen isn't that formal, but it's very intuitive. Like no two nodes will ever output leader because that would be bad. So something that is wrong shouldn't happen. And liveness is kind of the opposite. Something good will happen eventually. In this distributed paradigm, you have no idea what's going on. There's so much going on. You basically can say like, we want it to work and we want it to don't work. So something good will happen eventually. It may take a very, very long time because distributed computing is very hard. But we want to be able to say like, as long as nothing goes wrong, which was our assumption from before that there are no failures, like this will not get into like an infinite loop type of state because that would be bad. So something good will eventually happen is kind of, I don't know, they're kind of similar. Saying something good will happen means it won't get into like an infinite looping state or something like that. So these are kind of the two things we think about. So for this application, safety would mean no two different nodes output leader, and liveness would mean every node outputs something because that's good. If everybody is able to come to some decision. And if you take those two things together, it kind of makes sense that that's enough to prove correctness for this algorithm, right? If everybody comes to a decision and the decision is not wrong, then it's right. So that's a good algorithm. So yeah, so it's fairly straightforward to prove that Chang-Roberts satisfies both of these conditions. I kind of talked about it a little bit before, like no two nodes output leader because there's only one minimum ID, right? So nobody's going to receive their ID back. If they have the minimum ID, that's the one leader. So no two nodes will output leader. And every node outputs because there are no failures, and everybody will receive the terminate message if they're not the leader. Okay, so this is, I'm going to kind of give an introduction to big O analysis because big O analysis, if you've never heard of it, is kind of like a huge foundation of theoretical computer science. Basically, the idea is you want to be able to analyze the runtime of algorithms. Like, how good is this algorithm? Is it fast? Is it slow? How much faster can it be? You want to be able to say, like, formally, strictly, like, maybe this is the fastest we will ever be able to make an algorithm like this. And so, how can you instead of getting into the really nitty gritty of like all the details of like someone look at my C++ code and tell me like, is this the best? Like that's really hard and people don't want to do that. So you want to be able to say like, kind of really quickly and correctly, like, is this a good algorithm? So Big O doesn't worry about kind of small details like what programming language or anything like that. It focuses on the asymptotic runtime of a program based on the input that you give the program. So Big O, you use a Big O, and N is usually like the size of the input. So like, I don't know, maybe if you say like there are N nodes in this ring of nodes in the distributed system, maybe there's 100, maybe there's 1,000, whatever. So when you say it's O of N, that means if you doubled N, you would double the runtime of the algorithm. So the bigger the problem, the harder it takes. Like it's kind of obvious. Like if it gets 10 times more nodes in the problem, it'll take 10 times as long to do, roughly. But Big O doesn't really care. Like maybe it's a little bit, some algorithms are a little bit slower, some are a little bit faster, but it's roughly if you double the input, the output, the time it takes to get to a solution doubles. So O of n factorial is very it's a function that grows very fast. So asymptotically, like if you look at the end of the function, that's going to be a huge number. N factorial goes up super fast. So that's like an example of a really, really slow algorithm. Then this is kind of like the details. Like if you had an algorithm, maybe it looks at every single node, but it looks at every single node twice. What's the difference between an algorithm that looks at every node or an algorithm that looks at every node twice? Like in our example, we went around the ring a few times, right? Like the leader sent the message all the way around the ring, and then it had to send the terminate message all the way around the ring again. Maybe I'm getting a little bit ahead of myself, so we'll get to the Chang-Roberts analysis in a sec. But this is just an example of like not caring about the nitty-gritty details. O of n squared means if you double the size of the input, it'll take 4 times as much time to get to the solution. And in Big O, we don't care if it's we don't care about constants because that doesn't really affect like the asymptotic rate of growth. Maybe it's like a line, like one line versus a steeper line. They're both lines. We care if it's like a steep upward curving line. So these are all the same under Big O. We don't care if it's times a huge constant. If there are other things like n log n is if you think about n log n doesn't grow as fast as n squared because log n is less than n, so n times n, of course, is more than n times less than n. Yeah, so like the n squared term dominates. So I'm just realizing this should be c times n squared. That's a typo. These are all equivalent if this was n squared. So this is like kind of a, yeah, this is like super important for computer science because a lot of things operate at a huge scale. So being able to know like if this is an algorithm operating at the scale of the internet, having some like napkin math to determine like, is this going to take, maybe a day or maybe 100 billion years? Like that's important. Does this make sense to everybody? This is like, I don't know, really brief introduction. If you're new to this, you're going to see this a lot. For those of you that are in CS and even in math, like this is like super important. It's not super important that you have a deep understanding of it right now. But this is just kind of I don't know, I figure this is the first meeting. It's a good chance to kind of introduce people to something as important as this. And we're going to see it applied in a minute. Okay, no questions.
Why is everyone squared equal to O of C times N?
It's not, that's that. There should be a square. This should be square. Yeah. I wish. Okay, so Big O for Chang-Roberts. How fast is the Chang-Roberts algorithm using Big O notation? So first we're gonna look at time complexity, which is the number of messages between the start and the finish. So does anybody have an idea of what is what is the time complexity of the chain route? Yeah,
For that,
of n. What makes you say that?
because so it goes to the chain once to get to the entire chain. So that would be n computers that would have to go through. Then going back would be another n, but the constant number matters because of that.
Yeah, exactly. So the smallest ID travels, just like you said, starts at the one that will become elected leader, the smallest ID, goes all the way around the ring. It decides it's the leader, sends the terminate message that goes all the way around the ring again, and then it's done. So that's 2n roughly messages to go all the way through all of those n nodes twice. We don't care about the constant, so it's just open. Okay, so what about this is just like a little wrinkle. I think it's a little bit interesting to think about. Like, what if you had another node start an election like at the same time, like a little bit later? Like maybe it's not okay, actually, okay, I'm getting a little bit. There's a few things going on. There's a lot of interesting things just in the simple example that could happen. So first of all, what if the node just after the smallest ID starts the election, right? Any node could start the election. So actually, if that node starts the election, then it'll have to go all the way around the ring. Just before it gets back to where it started, it meets the lowest ID, which then determines that it's the leader, which then it'll have to go all the way around again until it gets back to the leader, so that the leader can decide that it's the leader, and then it has to send the terminate message again. So it's actually closer to 3n total messages that it might take to go all the way around the ring 3 times if you start right after the leader. But still, it doesn't matter. Still big O of n, because it's 2n, 3n, doesn't really matter. So that's, I don't know, that's one interesting thing. Another interesting thing is like, I said different nodes could start the election at different times, right? So you could start one node could start an election and it could start sending messages around the ring, and then another node starts sending messages around the ring at the same time. But if you think about it, they don't necessarily even really know that happened, and it still kind of works, right? We didn't really think about this with the safety and liveness, but when we were kind of saying like this algorithm is correct by looking at safety and liveness, we kind of covered this, like even if there's those extra messages being sent, if 2 different nodes start an election at the same time, like eventually it will come to some stable state, right? Because they're all sending messages through each other. So I don't know, the second node to start the election doesn't really know and doesn't really care. Like maybe its message went all the way around the ring, or maybe some other node started sending its message. But still, the time between the start and the finish of one of these running algorithms is still like it's impossible for it to go around the ring too many times. I don't know, that's kind of hand wavy, but just kind of wanted to kind of bring it up because I think it's interesting. Okay, so message complexity. So this is still the number of messages, but it's more number of messages in total, not like between the start time and the finish time. Does anybody have a guess as to message complexity?
My intuition says O squared, but I don't have a very strong justification for it.
Okay. Why does your intuition say that?
I feel like in the worst case, we might have so that each node's messages makes it almost all the way around.
Okay, so each node, okay, so
Like if the nodes were arranged in like strictly like in ascending order.
yeah. So if every node starts an election at the same time and the IDs are all ascending, that's the case where like if there's a node, like that ID will have to get dropped at some point if it's not the leader. And maybe that point is right beforehand if it's ascending. So if it's ascending around the ring, the one that's smaller is all the way right before it. So it has to go all the way around, and all of them will be sending those messages all the way around. Yeah.
I'm not sure I completely see understand the difference between time and message complexity. What does start and finish mean?
Yeah. I was kind of hoping someone would ask something like that, because it is like number of messages between the start and the finish, or the number of message total is kind of a bad way of putting it. Because like isn't the number of messages between the start and finish the number of messages total? Like, the idea is with a distributed system, you can have a lot of things, a lot of different things going on at once. So maybe if every node sends a message at the same time, the amount of time that takes to happen is still only the worst case time for one of those messages to be sent. But you still had n messages being sent. So yeah,
So it's the number of messages that have to be sent between the start and the finish that have like a data dependency on
Yeah.
each other.
yeah, exactly. So like you could have like I don't know if there's a bunch of nodes in this ring. I don't know, this isn't gonna be exactly related to this problem, but like if you had, I don't know, this is the start and this is the finish of something. Like this took 1, 2, 3, 4, 5, 6 messages to get from the start to the finish. But like, I don't know, maybe there's also other messages being sent by this algorithm. Like, I don't know. Something like this. Like these are, and maybe these are required to get to like
That's what IP traffic looks like.
So like maybe, I don't know, maybe these messages are required to get to the finish, but like this path from here is like 1, 2, 3, 4, 5. So like maybe these were important messages. Like there are like maybe this is a different algorithm that's running. Like these computers might be talking about something else. We don't care about those messages. We care about the messages involved in this algorithm. But this path of messages is only 5, and this path is 6. So if the algorithm requires all 6 of these messages, we call that the time complexity because that like takes more time. And this other version is not making it take longer, but it's still using up network bandwidth. So the message complexity is more for like usage of network bandwidth. Yeah.
Okay, I have a really stupid amateur's question, which is why would you need to implement this algorithm? Like, why do you need to call elections? Why can't I just say, this is my favorite computer, this is the one who's in charge? Like, and obviously I understand that in the real world, sometimes your favorite computer blows up or just gets disconnected or whatever. So you need to do that. But in this case, we assume no failures. So like, suppose we live in no failure land. Is there ever a reason to do this, or is it just about the fact that sometimes your favorite computer blows up?
That's a good question. Yeah, so definitely, like what you're saying, like if your computer blows up, like that is in the real world, that is definitely a very real problem. Like a lot of things go wrong, and if you have a system with like a million nodes, like one of them might just break. So you could try to spend a lot of money to try to make sure this computer is really good and never gonna break, but like it probably will break at some point. So in the real world, yes. So, but to answer your question, like if you're in this fairy tale land where nothing breaks, I don't know. And like if you're making up fairy tale land, you might as well just make up whatever you want. Like we don't need to do computation. We already have the answer. I don't know.
Computer isn't the same as everyone else's favorite computer. And the
Well,
other
okay.
people own the other computers.
Oh, if other people own them, yeah, okay,
Look.
that's fair.
That
Yeah.
does actually sort of lead into a question I had, which was, if I understand this correctly, if during an election, a computer changes its ID, everything breaks.
Sure.
So haven't I implicitly, perhaps not consciously chosen, but randomly chosen my favorite computer during the assignment of their unique IDs, which can't change otherwise because that I don't know when an election might be in process. And if I stay the same, I will always elect the same leader.
Right. So yeah, so you kind of, I think what you're getting at is like these IDs can't change. It's a fixed unique ID because otherwise it breaks. But there's kind of two sides of this. There's like the math side of this where like we're like in math, you can assume you know everything. But in the real world, like you can't assume that. And like the study of this topic, like each process knows only its ID. It doesn't know, like maybe it doesn't even know how many other nodes there are. Like this algorithm, like you could have, I don't know, you only know your neighbors. So
I guess if we assume that nodes might get added or removed, and we have some other algorithm that constructs the logical ring, then even if the IDs stay fixed, who we elect as the leader might not be. So I suppose that's a
yeah.
reason where the algorithm would still make sense, even
Yeah.
with static IDs.
And like maybe what's important is that each process is bringing its own ID to the table. It's not like maybe if there's some other algorithm that constructs the ring, it's not assigning the IDs. If it were assigning the IDs, it would just assign a
It could
leader.
just assign the leader.
Yeah. So there's something different about these nodes that it's bringing to the table that it uses. And it's an abstraction. I don't know. But yeah.
Or the on applications, I don't know much about data systems actually like operating them. Really mentioned like designating the communication node in a center. I was thinking like assign. You could assign the election IDs to all the nodes in the cluster based on like message latency, like the amount of time it might take for a message to get from any given node on the center to another center or something.
Yeah. Yeah, it doesn't need to be an arbitrary ID. It could be some ID that's actually like maybe gives that node a better shot at being a good leader. Yeah.
Like,
Okay.
Save any.
Okay. Okay. Yeah. Okay. Maybe I'll just there's not I was just gonna brush through this next algorithm, so it's kind of I'll just still brush through that anyways. So there are this isn't the best algorithm. There are other algorithms. This example of I'm not gonna read through all of this just for the sake of time, but the idea is with this algorithm is kind of to use this ring almost as like a binary tree, like that you can start getting like a binary tree, you can get log of n complexity because you're like abusing the structure of the tree. So what if you said that in your ring you just went by progressively increasing length or like size of the neighborhood. So like let's say this node is its first neighborhood is just itself. So it says, okay, I'm the best in this neighborhood of just me. Okay, so now I'm gonna look in wider neighborhoods. So then it looks in this neighborhood. And then it sends messages out to both sides. And then like, okay, so it sends its ID both ways. Let's say it's lower than both of its neighbors. So then its neighbors are like, okay, wow, have a lower ID than me, you win. So it sends that message back. So this node now knows that it won this neighborhood. And these nodes know that they are losers. So they are going to stop sending messages. Or they're going to stop initiating their own neighborhood elections. But then this node knows, okay, it won its election, so it's going to double the size of its neighborhood, which now brings it all the way over to here. It's going to send those messages out to its neighbors, and then like same thing. It sends its messages along the neighbors. If this has the lowest ID, it sends its messages back, and then these nodes know to stop transmitting, and then this one doubles the neighborhood again, so that it sends into a neighborhood all the way down to here, or something like that. I don't know. This is really rough, but I don't know. Then it gets a bigger neighborhood, and then maybe it wins that election. So it goes progressively larger and larger and larger. That idea, I hope, kind of makes sense. The correctness, yeah, it's kind of saying like if there's one thing that can win every election, then it can win all the elections, so it'll be the leader. Kind of okay, yeah. It's correct, trust me. So this seems like much more complicated. So like, is it more complicated? The time complexity is not more complicated. It is more complicated. It does take more messages, but it's still asymptotically linear, so it's still big O of n. Like it still only is going to go around the ring. Like it's going to go around progressively larger rings, but because of the growth rate, it's still, it's not that bad. But the message complexity is what we improved on. So yada yada yada. It's like a binary tree. It kind of grows at a like an exponential rate, so it can get log n message sending. Which maybe it's more messages on a ring this small, but if you have 1,000 nodes or maybe 100 million nodes, like maybe there might be a huge ring. You can get better complexity. Hopefully that made sense. If not, the slides will be posted in the Discord. And you can feel free to come up to ask me questions right now, if you want. But yeah, there's some more to it. You could have like, why would you choose to arbitrarily construct this something like, why would you use a ring? Why not use something better? There are some reasons. I don't know, notably, there's like Cassandra, which I think was Facebook. I think it's open source maybe, but like, I don't know, it's just like there are some actually uses of using a ring, and you actually might want to do something like this in the real world. It's not just like made up. Let's use a ring. Okay, yeah. So bibliography. Thanks for coming, everyone. Hope to see you next week.
Okay, just like a brief admin announcement, how Sigma usually works is we'll have we have the admin present the first few weeks, but then after that, we open it up to any members. So if any of you are interested in presenting on any topic within CS theory, it can be whatever you want. Although people do get mad when you try to present on quantum, apparently, but yeah, if anyone's interested in presenting, please reach out to one of them.
And we can help you find a topic or make a presentation if you're interested. Yep.